So binary search tree is obviously a tree, right? So what is a tree? Tree is a hierarchical structure, right? And we have seen this
Yes, sir.
before, right?
Yeah.
It's a non-linear data structure, right? It's a non-linear data structure. Okay. Um, and here you have nodes, right? The parent,
Mm-hmm.
you call them parent node, and it can have multiple children, right?
Yeah.
Um, Now, if you talk about BST as such, okay, so it's, as the name suggests, binary. Binary means each node can have maximum 2 child node only. Okay,
Mm.
and uh, okay, so nonlinear data structure, it have each node can have max of 2 child node. Okay, and important thing here is that left side values of node will always be greater than, no, left side will always be smaller than, right? Not greater than. Smaller than the node, and right side will always be greater than the node, right? This is important property of your binary search tree. Now, if I draw a tree, okay, let's say I draw a tree. Um, let's say I take this and node. Okay, I draw a node here and I say it is 50. Okay, let's say I add 50 here. Now to this, if I have a child node or children, okay, I can have something like this. If it is 50, it has to be smaller, let's say 30, right? And this has to be greater, let's say 70. Okay, so this is a BST, binary search tree, because the root node is greater than the left side node, greater than the right side node. Now, let's say this one also has 2 nodes, for example. Okay, and we'll assign values to this, let's say 90, to this, let's say 60, okay, to this, let's say 20, to this, let's say 40. Is it a binary tree?
Yes.
You think so?
Yeah.
So, this is how you represent it. So answer is no. Okay, it is not a binary search tree. Why? You see this 40? So, okay. Uh, my intention was something different. Okay. Yes, it is a binary search tree. Okay.
Mm-hmm.
It is a valid binary search tree. Now, if I make this as 55, let's say, then it is not. Okay. Because root node is 50, all these values have to be less than 50. Is it indeed? Okay.
Mm-hmm.
So yes, 40 was, okay, but 55 is not. Okay. So this is not your, okay, this is not valid one. Okay. I was thinking mentally to write 55. Okay.
Mm-hmm.
So this is not your perfect BST, because
Yeah.
the left side of 50 is greater than the 50 itself.
Mm-hmm.
Okay. Okay. Why do we do that? Why do we create a BST? BST is is easier to search for values. Okay. Is easier to search for values. Okay. So, um, okay. um, searching using BST is always easy. That's why when you one of the examples of the application where it is used is when you manage your indexes in database, right? So we know that indexes are created based on the primary key. Okay, and the primary key values is search using BST. Because when you start from the root node, you know which side to go, right? If in this example, okay, let's say you have a value, let's make it as 45. Let's assume this is 40. Now, if you have a value 75 to search for, right? Then when you start, you see 50, you know that it has to be on the right side. Okay, you see 70, then you know that it has to be 75 has to be on the right side of 70, right? So it becomes faster. You're able to search faster. That's the main primary application of, that's why its name itself you have search. Okay. Okay. It drastically increases the performance of your search. And also the insertion deletion is faster compared to your queues or queues. Okay, stack and queues, let's ignore because there are special cases. Linked list, for example. Okay, the insertion deletion here is much faster compared to your linked list. So that's why we prefer binary search tree, whether it is to search, whether to store values. Okay, this is very important. Now, how are these trees created? Okay, so let's see the steps. Okay, now let's say I have to create a tree based on some values here. Let's say I create here 50, okay, 30, 10, 70, 90, 80, 15, 25, 35. Okay, let's say these are the values. Okay, so when you get the values, okay, first you have to create the binary search tree, isn't it? The tree. Then we will search for the values. Then we will see how to do insertion deletion. So in trees, you have four important operations. Okay, we'll talk about operations. First, it's a creation of the tree, right? Because creation of a tree will solve most of the problem. Then search, then insert, update, delete, right? These are generally the operations we need to generally perform. Okay, so let's say here you have these numbers. Okay, so first anyway, the first node will take, and you have only one value, one node. So obviously it's going to be 50 at the top, right? So you have 50 at the top. Okay, then what happens? Then you read the next element. Next element is 30. So if this is smaller than root node, then insert the value to the left of the root node. So you need to have one more, right? So you read 30. So 30 is smaller than 50. So where will 30 go? On the left of root node, isn't it? So you have to say 30 here. Then you go to the next element, 10. Okay. Then 10, again you compare with root node. 10, it has to go on the left of 50. 30. Again, it has to go on left of 30. So you create, okay, you create one more value. Right?
Yes, sir.
Makes sense? So what I'll do, I'll put 10 here. Next is 70. So where do you put 70? 70 should go, compared with root node, it has to be on the right side. 70. Okay. Okay. Now what you have after 70, 90. 90 should again go right of this, right?
Mm-hmm.
Correct?
Yeah.
After 90, you have 80.
Mm-hmm.
So 50, 70, 90, 80 should come here. Yes? Then it's 15. 15 is less than 50, is less than 30, comes here, but is greater than 10.
Mm-hmm.
So your 15 will come right of 10. Okay, let's use this sticks. Okay. Okay. So far, this is our tree. After 15 comes 25.
Mm-hmm.
So again, compare with 50, okay, is greater here, now greater than 15. Okay. So you will have 25 here, right of 15. Then is 35. Okay. 35. It should come here. Yes.
25. What?
35.
35.
25 is here.
35 come to the right of 30.
No, 35 will come right of 30, isn't it?
Yeah, that's what I said, sir. Yeah.
Yeah. So that's what we have here, isn't it? Okay. This is your binary search tree creation.
Yeah.
Okay. So our binary search tree is ready. Okay. This
Mm-hmm.
is how your binary search tree is created.
Yeah.
Okay. So let me creation of BST. Done. Now comes how to search.
Mm-hmm.
Okay. How do you search a value? Let's say I want to search for okay, I want to search for 45.
Mm-hmm.
I want to search for 45. So you start from 50, compare the root node with the value that you are searching for.
Mm-hmm.
45 is,
Less than 50.
so you should go on the left side.
Yeah.
Now you get what? 30.
30.
Okay. Now 30, is it
Less
greater
than 40.
than the target variable?
Less.
Less. So 45 should have been on the right
Right.
side. You come here, you get 35. Okay. Now 35 and 45. 45 should be on the
Right.
right side. But do you think, okay, 45 would have been here?
Yeah. I mean, no. I mean, yeah. It could be like, it depends on how you make it.
No, it will be here. It should have been
It'll,
here.
yeah, it'll be there. Yeah.
Correct, because 45 is greater than 30, right? It should be on the right side.
Yeah.
And 45 is less than 50, right? It should be on this side.
Yeah.
So now when you reach and when you say, okay, 45 should be in the right side of 35. And what is the right side of 35? None,
No.
null, right? So you
Mm-hmm.
reach, so while you reach till the null value, okay, and if you are till you reach null, and if you're able to find the target variable before you reach null, then you say available. In this case, this is not available,
Mm-hmm.
right? Now, if I search for 25,
Which one? Which number is it?
25.
25, 20, first you go to 50, 25 less than 50, then you go to 30, 25 less than 30, then you go to 10, 25
So
greater than
30
10,
left side. Again, you
and then
go for
right side and
greater
then right
than,
side.
and finally you'll find it.
Yeah.
Okay. This is how the search is done. So you will find. So your root node should match. Every time you're comparing root node. Okay. And the root node is, okay. So if root node doesn't match, then you go with root node of left or right, depending upon the value, or until you reach null. Okay, so end of every these values, okay, you have null, 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 right? So this is how you perform search. Okay, now how do you delete an element? So to delete an element, okay, your okay, to delete an element, okay, there are three possibilities, right? You're deleting about root node. Okay, now let's
Mm-hmm.
say deletion and insertion we'll talk about.
Mm-hmm.
Now to delete, there are three possibilities. Okay, so delete, again you have to search and check what value you have. Is it leaf node? Leaf node means no child node.
Mm-hmm.
Now if there is no child node, it's easy, right? Just delete it.
Yeah.
Okay, the previous node, whether it's left or right, set it to null. This is deleted. So if I have to delete 25, okay, if I have to delete 25, I will go with this node and I'll say this node of right equal to null. 25 is deleted. Otherwise, you will have a node with one child. What happens when you have node with one child?
And just you delete the first child first.
Okay, so let's take example of 90. Okay, so you want to delete 90. So what you do, you bring 80 to 90 and delete 90. Will it work? Yes.
Yeah.
Right? You bring 80 to 90. So let's say we'll take two examples, right? One child means it can be your left side or right side. So if it has right child, left child here, in this case 90, 80, you bring 80 here and delete 90. It works? Yes, it works fine. Okay.
Mm-hmm.
Now, if you delete 15, let's say 15 has right child. So if I bring 25 here and delete 15, will it work? Absolutely. Okay. So absolutely no problem. So deleting leaf node is easy. Deleting node with one child is also easier, just that you have one extra step where you have to bring that child to the node. Promotion. You're giving promotion to 25. 25 will come here or 80 will come here. Or 35. Now, the question is, when you're deleting node with two children, that's when the problem comes. Okay. If I delete 30, if I delete 30, if I have to delete 30, I will have to bring 35 up here. And see, all these examples I'm talking about one node is all like leaf node, right? Leaf 35 leaf node, great. But if I have to delete 70 here, let's say, or let's say I have to delete 50 itself, let's say. If I have to delete 50 here, then what should I do? I need to bring 70 here,
Yeah.
right? And rest of the relationship, will it be same?
I mean, it'll like move to the left. Like the right side of the tree will move to the left. Like not to the left side of the tree, but like it'll be 70, then 90, then 80, like that.
Yes. Okay. So, okay. So this is how, okay, deletion will work. Now, if I have to delete, insert something, same operation.
Delete what, sir?
No, insert. I want to insert something now.
If you want to insert something, same, you have to search for the two nodes that are right below it and above it and insert it between those two, right?
Yes. Right? So
Yes.
now let's go and see the implementation, right? Shall we?
Yeah.
Okay. So let's do that. So insertion again, when you try to insert, you have to first search and find the position, and then everything should move to one step lower, isn't it? So let's start with simple one. Let's create the binary search tree, and then we will learn how to delete and insert. So let's go back to our program here, and I'm going to first create a binary tree. So I call it as class BST. Okay. Now you define init. What all things will be in init?
Node, like the first node, head node.
Okay.
Yeah.
So you need to give the value here, right?
Mm-hmm.
And so you have three values here. Okay. Just like your doubly linked list, you have three values here. Okay. First will be, of course, the key itself. So I'll say self dot value equal to value. Then self dot left and self dot right. Okay. So self dot left. Okay. By default, let's put it as none. Okay. Self dot right is going to be none. So your binary tree is ready. Right?
Yes.
Okay. Next, we are going to do let's do so let's call this class first. Okay. Or we want to search for the root node maybe. First, let's do the binary search. Okay. Then we can do insert as well. Okay. So how do we do search here first?
We have traversed through it basically, right?
Yes. Okay. So but before we do search, right, we have to create, right?
Yeah.
right? So I'm just thinking which way to start. Because see, whether you do search or you should do deletion, your data should be ready, your tree should be ready. So obviously, first thing you have to do is insert,
Mm-hmm.
right? We have to do insert. Okay, so let's work on insert first. Okay, so I'm going to say def BST insert. Okay, now your insert, okay, we need to pass the key, right? Which value you want to pass.
Mm-hmm.
Okay, now first thing you have to check is if the node is if the node um, is null. If node is null, okay, so instead what I'm going to do is let me not put part of the tree or class, we'll put it differently, insert here.
Mm-hmm.
Okay, so I'm just okay, so here we'll pass key and we can pass the node.
Okay.
Okay, and now we will check, okay, if this node is none. If node is none, what does it mean?
There's no value.
There is no value, right? So you can
Mm-hmm.
simply say return, okay, our BST. Okay,
Mm-hmm.
there's empty tree, okay, and we are adding our first value.
Yeah.
So I'm going to say return BST of key. Okay, done.
Mm-hmm.
Now, if okay, okay, so this is node, the root node. Basically, you're comparing about root node, okay, or let me
Mm-hmm.
use the word root here. Oh, see, this insert will keep on repeating. So let it be node only, because again, we have to check. First, you check with root node, then again, we'll check with another node, so on, right? Now here, I'm going to call all these. So let me say if name, okay, equal to main. Okay, if name equal to main, then first thing you have to do is you have to create root node. So I'm going to say root node equal to none initially. Now you want to add it. So root equal to BST insert, right? BST insert, and I'm going to add root. Root will always point, just like in linked list we had start. Start will always point to the start. Here you will always have a pointer to the root node. That we cannot lose, right? Now I'm going to add 50 to it. Okay,
Mm-hmm.
insert 50 to it. So now when I call this function, what will happen? Okay, so your root node is created, correct? Root node is created, isn't it? Okay. Next, if I add one more, okay, I'll say here BST insert, okay, I will add the root node and then I'm adding, let's say, okay, let's copy the same code that we had it in the PPT, right? One second, let me copy from the PPT. Oh, I have to save this. I forgot to save it. One second. I'll just save it. Okay. And then I'll go and copy the same data. So we are here. Okay. So 50. After 50, we add 30 to it. Okay. Now this
Mm-hmm.
is not going to work because root node in this case is not none, right? Because root has a value here.
Yeah.
Root has some value here. So obviously it's not none. So what we'll do is here we'll compare what Okay, if root dot value, if root dot value is less than the key. Okay,
Mhm.
if the root dot value is less than key, then what we do?
Um,
So we will say here, okay, why I'm using root here? It's node only, right? We are renaming it as node, isn't it? So node dot value is less than key, okay?
mhm.
Then we will say node is less than key. Node is
Less than key.
less than key. That means this value should be added on the left or right?
Side.
Right, correct.
Or side. Yeah.
Should be on the right.
Yeah, right.
Because
Yeah.
see, key is greater, that's what it means.
Mm-hmm.
So you'll say node dot right equal to, now we will again call this BST insert. Now this node is node dot right.
Mm-hmm.
Node dot right. Okay. First is key. So RIGST node dot right. So first we'll add the key here. Key comma node dot right. So key will be the value anyways. And node dot right in this case is none, isn't it? Because node dot right is now node. First time it was root and you are iterating either left or to the right. Here we went to the right. So here your node dot right is none, isn't it? Because the root node does not have any value on the right.
Mm-hmm.
So key is added to this now. Makes
Mm-hmm.
sense?
Yeah.
Okay. Now, same thing we can repeat. Now we are assuming that there are no equal values. Okay.
Mm-hmm.
Okay. It's like you don't have duplicate values here. That's what we are assuming, right? Like if you talk about primary key, you can't have duplicate values in primary keys, correct?
Yeah.
Now here, if node value is greater than key, then we say node dot left. Okay, node dot left equal to binary insert. Okay, node dot left.
Mm-hmm.
Okay, once you are done, you return node. Okay, and with all this recursiveness, okay, we are hoping that this node will have all the final values now,
Yeah.
right? So you can do this. Now, let's say, okay, now let's start building this root, this tree. So you have root, okay, so
Mm-hmm.
30. Now let's keep on adding. So how many times I have to do? 50, 30 is done. 3, 3, 6 or 7 more times. 1, 2, 3, 4, 5, 6, 7. Okay, 5, 30, 10, 70, 90, 80.
Yeah.
90, 80, 15, 25, right? 25 and 35. Okay.
Mm-hmm.
I think we have given reverse where line number 19. Root and number. Okay. First is key, then node, right? See. We are first giving. So, okay. So what we'll do is we'll change it better. Instead of changing so many things there, we'll first put node and then we'll put key. And here also we'll put key after the node.
Mm-hmm.
Okay, now hopefully it should work. Great. So we have built our
Tree.
tree. Now let's search for the value first.
Okay.
Okay, we'll search for the value first, and then we'll look at other aspect. Okay, so if I start searching here, okay, um, okay, so let's write our query again, I mean function again, def BST underscore search. Okay, and here we also need to find the node. Okay, and in this case it is not recursive, so we'll put root node only direct. We'll call it as root, comma, the key, the value that you want to search, target or key or the value.
Mm-hmm.
Okay, now we need to perform the loop here. First of all, we'll check if root is none. Okay, root is none, or let's say, okay, if root is none, we can return none, or if root itself, root dot value
Mm-hmm.
is equal to key. That means first thing itself double equal to, right? Itself is the key. So we're
Mm-hmm.
returning root. Okay. So see, in case if root dot key is a value, okay, root is returned. If root is none, okay,
Mm-hmm.
then none will be returned, right? So in either case, returning root only. So this is okay. Now, okay, so now for the search, we have to check if it is not equal. That means if it is greater or less, then what do we do? Okay, so
Mm-hmm.
now we'll check for value on the left side. Okay, so we'll say if root dot key, is it key? No, value, right? If root dot value is less than our key, then what we do? We return again binary search. Okay, recursive. And if root dot value is less than key, root is less than key. Again, right side thing. We have to go to the right side. So you go to root dot right. So in fact, here node is better than the root.
Mm-hmm.
Let's use node only. Root is one time, but here. So we are saying go to the right, node dot right, and check with key there. Okay. Now again, we will say here if node dot value is greater than key,
Mm-hmm.
then node dot left, right? Now this will return either the root or none, right? So
Mm-hmm.
we will, okay, so let's say here we will search for the key here. Let's say key equal to, first we'll have some positive thing, let's say 70. Okay, so you
Yeah.
will say uh, uh, is found or something. Is found equal to, okay,
Mm-hmm.
BST search, BST search, okay, and we'll pass the root and the key, isn't it? Done.
Yes.
Now, if is found is none, then you say print value not in the not in the BST.
Mm-hmm.
Okay. And if it is not, right, else you say print value is found in the BST. Right?
Mm-hmm.
Let's do one with 70, and let's do another with something which is not there. 75, let's say. And I can put value here, correct? So okay, key. I'll copy and paste everywhere. Value key is found, value. 70 is found in BST, 75 is not found in BST. Right?
Mm-hmm.
So this is how search has worked. We'll stop here. We still have to do things like, you know, insertion, deletion, and displaying the tree.
Okay.
So what you can do is, okay, you can write a menu option just like we did in the linked list, right? Circular linked list we did. So create a
Yeah.
menu option for all these options, okay, build and, okay.
Mm-hmm.
You can do this using a loop, right?
Yeah.
You can, read this, so input value as a list and put it in a loop and keep calling this insert till the list is finished, right? Till you have managed or you have put all the values from the list here.
Yeah.
Then perform all these using menu option. Next time when we meet, we will talk about insertion, deletion, and displaying the list. Of course,
Okay.
we can't display the list in a tree structure.
Yeah.
Okay. But what we could do is do option one, we display like a infix kind of like left. Okay. So
Mm-hmm.
again, you can have like infix, postfix, prefix. Here also you can have
Yeah.
left node, left, center, right, or center, left, right. So you can display as left, node, right. Okay. So node will always be in middle. So if you take, if let me go back to the uh, our presentation here. 1 second. Okay, so 50 will be in middle. All these values will be on the left of 50. So 30 will be middle of 10 and 35. Okay, 15. So here, if I have to display left node right, okay, the output, the display value would look something like this.
Mm-hmm.
Okay, now here 10 should be in the center and 15, 25 should be on the right. Okay, so
Okay.
10 will come here, 15, 25 will come here. Since there's no element on left of right 10, you don't have any value on here. So
Mm-hmm.
10, 15, 25. Now comes 10, 30, 35. So 10 left, 30, 35. So now you get 30, 35.
Mm-hmm.
Okay.
Yeah.
Now 50, this all should be on the left of 50. So all these are on the left of 50. Now comes 50. Okay. All these values should be on the right of 50. All these
Okay.
values are right of 50. Now you look at 70.
Yeah.
So 70 should be in the center of left and right, but there is nothing on the left. So 70
Mm-hmm.
comes here.
Okay.
Okay. Now look at 90. 90 should come after left and right. Should be between left and the right. So yes, you have value on the left. So you get 80. Okay. 90 and nothing on the right because there is no child on the right.
Yeah.
So this is how you display. Now you see here, do you see any, do you notice anything here?
Yeah.
It is sorted.
Yeah.
Okay. So what we did, we put left, node, right. This is your left, node, right, way of reading the value and displaying. Now I can do like node, left, right. Left is always left of right. Okay. So either you do left, right node or node, left, right. So if I do no node left right, then it should be 50 left node and right node. Okay, so it's going to be like 50, then left comma right. Now, if you look at this left, you have 30 left and right. So it'll be 30, okay, left right. Now this is different left right, okay, not confused with this. So 30 left right. Now in left right you have 10 and 35. So left will be 10 left, and this right has become 35. Now 10 left, there's no left, right? So here you'll put right. 10 left, right. So there's no left, right. Now you have 15 and 25. 50, 30, 10, 15, 25, now 35. There is nothing on the left. So 35 will come alone. So this is node left. Now again, we have to expand right. If you expand right, okay, so node is 70. So 70 will come here, and then left side. There's no left side. So then right side. In right side, 90 is again node. So 90, now left side, 80. This is what you will see. Okay, you can again compare. Okay, I might have gone some small mistake I might have made. You check it. It's node left and right. So your node left and right, this is what you get output. Okay. Similarly, you try left right node. Okay, left right node. Okay, in left right node. Okay, so first left, then right. 50 will be at the last. Okay, then 10 side 35, 30 will be at the last. Then here in left, okay, 15 will be at last, 25 will be last. So 25 last, 15 last, okay, 10. So try to build that and we will see. Okay, but this is the general, okay, this is the normal what we do. And if you see, the elements are sorted automatically. So you can create a BST and read like infix kind of thing where you have row in between, data will be sorted. Okay, so this is how you can sort data using your BST. Sorting using creating a binary search tree. Okay, we'll stop here for now.